Okay, hi everyone. So now in this video, we're going to look at some results with respect to continuous functions on a metric space. So in this particular example, we want to prove by the definition of continuous functions or by the definition of a function is continuous at a point that this given function, f from r to r, given by f of x equal x squared, is continuous um, on R. So it's continuous at every real number. And since they did not tell us what the metric is, and we are in the real numbers, we can assume that we are working with the usual metric. So before we get started, let me just recall the definition of continuity. Okay. So we say that a function with mapping f from x to y, and of course I'm assuming that x and y are metric spaces, um, is continuous at a point, let's call it x0, and x0 must be in the domain of this function. Okay, it's continuous at this point if for every epsilon bigger than 0 that you give me, I could find a delta or there exists a positive delta such that for any other point in the domain, so such that for, let me write it in a new line, such that for any other point in the domain and the distance between that point and this fixed point x0, so x0 is fixed here, with respect to the metric on x, because I have two metric spaces, x and y, so the distance from x to x0 with respect to the metric in x is less than delta. So whenever this condition is true, this implies that the corresponding distance of the function values, so the function value, the image of x, to the image of x0 with respect to the y metric, because the function values live in the y metric space, should be less than this epsilon. Okay, so this is the definition of continuity. And of course, it's continuous at a point. And if the function is simply said to be continuous and there's no reference to a point, then it is assumed it is continuous at every single point, which is what this example is asking us to show. That it is continuous at every single real number. So we want to prove that f of x equal x squared is continuous on all of R using this particular definition. Okay, so we want to prove this using this definition. So these proofs usually start off the same way. That is, let epsilon be bigger than 0. Then we could take or choose delta. Now you see, most books over here, or if you read proofs like this in a book, they will take delta and then they would put something over here. And it might depend on the function, it might be something very complicated. And it will leave you thinking, well, how did they know to even choose that delta? Well, the answer is they didn't. What I'm going to show you is we'll leave here blank and we're going to do the proof. And then at the end of the proof, it will tell me how to take this delta, right? So we don't know how exactly to take this delta, so we just leave a space there for now. And let's continue with the proof and see exactly how, let's try to find a relationship between epsilon and delta to fill in that part there. Okay, so I want to take a delta. I don't know how yet, but we'll figure it out such that, okay, so let me leave a bit more space. Such that 4. So now I'm just going to apply the what I want to prove here. Okay, so the left-hand side, the left-hand side here, what I want to prove, such that for x belonging to the domain, in this case, both domain and codomains are real numbers, and the distance, between x and x0, so I'm writing the left-hand side of this definition. But remember, we're in the real numbers with the usual metric. So the usual metric is just the modulus. So instead of writing d of x comma x0, let's just put what it is. It's modulus of x minus x0. And this guy is less than delta, implies, and what do I want to get? I want to get that the distance between f of x and f of x0 to be less than epsilon, but I need to show that it's going to be less than some epsilon. So I can't put down that just yet. So let me write out what this is. I'll move this to a new line to get some space. Okay. So this is modulus of f of x minus f of x0. Now I know what f is. F was x squared. I know what the function is. So I could plug that in here. So this is equal to modulus of x squared minus x0 squared. Now remember, x0 is fixed in all of this. And so this one has a little trick in it. Most of these proofs using having to prove that a particular function where they give you the equation is continuous at a point has like a little proof, has like a little trick in it where we want to essentially incorporate this fact here. I think I want to essentially incorporate this fact. So I want to see modulus of x minus x0. Now I don't have that. I have modulus of x squared minus x0 squared. Okay, but that's a difference of 2 squared. So I can replace that as x minus x0 by x plus x0. Okay, and this part here is, so again, I want to see x minus x0. So I already have one of the terms being x minus x0, but the second one I have a x plus x0. Okay, but that's not a problem because I could always write this second bracketed term as x minus x0 plus 2x0, right? It's the same thing. Okay, so it's the same thing there. And from there, I could use my rules of the modulus function to say that this is equal to modulus of x minus x0 by modulus of x minus x0 plus 2x0. Right, so from there to there, I'm using the modulus of alpha beta is equal to modulus of alpha by modulus of beta. Okay, I'm just pulling it apart there. And what I could do now is this second term. So this first term is fine because I have modulus of x minus x0, which is what I want to, or what I want to see. This second term, I need to break this apart. So I'll use triangle inequality for the second term. Right? So use triangle inequality on the second term to get modulus of x minus x0, right? Plus modulus of 2x0, but I'll pull the 2 outside one time. Okay. Now, so for this particular example, what I want to do is, so in this particular case, it makes sense to So essentially what I'm seeing here is that, so here's the problem. Here's the problem. This guy here is less than delta, right? By assumption. That's what I have, right? So that's good. This guy here is less than delta. That's good. The problem is this guy. This guy here is not necessarily bounded because if x0 is any real number, then I could just take x0 to be arbitrarily large. And then I can't bound this by anything because this guy here I can make arbitrarily large. Okay. But there is a way that we could do this um, by a clever choice of we could essentially break it up into two cases, right? And so I could say if x minus x0 is less than 1, why 1? Because if I have 1, then it will simplify things down a bit. So here's what I'm proposing. So you could say consider the case for whenever this guy x minus x0 is less than 1. Okay, so let me label this. Let's label this star. Okay. So from star, right? So let's just pretend for now that modulus of x minus x0 is less than 1. So from star, I will get that the modulus of f of x0 minus of x minus f of x0. F of x minus f of x0 is less than or equal. So will be strictly less than. So the first guy is 1 into 1 plus 2 modulus x0. Okay, so that's just equal to 1 plus 2 mod x0. So that tells me if I want this guy to be less than some fixed value epsilon, then what I will have to do is, if this guy is less than 1, I need to make this outer one, I need to make this, I want this to, I essentially want this to cancel with the 1 plus 2 modulus of x0. So if I had this, let's just pretend. So let's see what it has to be, and then we can write the proof neatly. So let's just say that this one out here was actually epsilon over 1 plus 2 norm x0, right? Let's just pretend. Then this will be less than this guy multiplied by 1 plus 2 modulus of x0, and this will cancel with this, and I will get the epsilon, which is what I want. Okay, so that tells me, so essentially what is that saying? That tells me that the inner guy being less than 1 is okay. The outer one, modulus of x minus x0, should be less than this number. Okay, so let me erase all this and I'll rewrite it. But let me put to the side. Let me put to the side that I want x. I essentially want two things to happen. I want x minus x0 to be less than 1, and I also want it to be less than this thing, epsilon over 1 plus 2 modulus of x0. Because when both of these conditions hold, right, I get everything canceling out and I get epsilon. Okay. So what that is telling me is Well, that's actually telling me how to choose delta, right? Because modulus of x minus x0 is less than delta, right? So if I take, for example, if we take, for example, delta to be the minimum of these two numbers, yeah, so that's it. 1 epsilon over 1 plus 2 mod x0, right? Then, so here, so let's check, let's see what happens. Then I know from up here that modulus of x minus x0 is less than delta, right? Modulus of x minus x0 is less than delta. I know that. Then since modulus of x minus x0 is less than delta, and delta is the minimum of these two, right? So this must be less than equal to 1. And what's the next possibility? Modulus of x minus x0 is less than delta. Delta is also less than epsilon over 1 plus 2 mod x0. In other words, by choosing delta to be the minimum of these two values, this one and this one, I could get both these properties to hold at the same time. I could get both inequalities to hold at the same time. Okay, so now, and since this and this hold, star gives the distance between f of x minus f of x0, right? So let me rewrite star is less than equal to modulus of x minus x0 into modulus of x minus x0 plus 2 modulus x0, right? And I know both of these inequalities hold because that's how I chose my delta. Remember the whole thing that you have freedom over is how you choose delta, right? So that's what we have freedom over, how we choose delta. I'm going to choose delta in a way such that modulus of x minus x0, this is less than epsilon over 1 plus 2 by modulus of x0. And we've also chosen delta in such a way that modulus of x minus x0 is less than 1. Okay, so from that I get this. So those two cancel out. This is equal to epsilon, right? And now that we know the relationship, we could come back here where we left our space, right? So where we left our space, take delta. How are we taking delta? Okay, let me write it in with a different color. Take delta. So now you see take delta equal to the minimum of 1 plus epsilon over 1 plus 2 mod x0 for this particular question. Okay, so that's how they get that delta. So if you're ever reading these proofs in textbooks and you see they take this delta to be, this weird, in such a weird way, and you're thinking, how do they know to pick this delta in such a weird way? That's because they did the proof first, tried to figure it out with a little, not necessarily rat, but like a little scrapbooking, like what I just did there to see exactly how to bound star, how to bound the inequality star. Then when you see exactly what you need, that will tell you one of the way in which to choose this delta. Okay, so therefore this function is continuous by definition. Okay, so in this question, we're going to go through the proof of one of the equivalent definitions of continuity. So far we looked at the epsilon delta definition of continuity. There's also one involving sequences. This one is the topological definition of continuity. Let's see, topological definition of continuity. Actually, in the area of mathematics called topology, in topology, they don't have any metric. A topological space is just a non-empty set together with a collection of open sets. So collection of or subset of the power set that satisfies certain conditions. So they don't necessarily have a way to measure distances between points in a topological space like we do in a metric space. However, continuous functions or the study of continuous functions lives in topology, not in real analysis. But there's, of course, a lot of overlap between continuous functions and many different areas of mathematics. So it turns out that if you that this definition, the topological definition of continuity, can be reformulated in the language of metric spaces to get what we are taking to be our definition of continuity. That's the epsilon delta definition. So I'm telling you that there are many different definitions of continuity depending on the space that you are working with and what you have to work with. For example, again, in a metric space, we have a metric. So we can measure distances between 2 points. And you don't have that in a topological space. So which definition of continuity is correct? The answer is they are all correct. They are all equivalent to each other. You could, once you make one of those as your definition, you fix one of those as your definition with respect to whatever space or structure that you have to work with, you can then use that to prove the others. So that is exactly what this theorem is saying. So it's saying let x and y be metric spaces and x be a function between them. So we live in a metric, or we are living in the world of metric spaces. So our definition of continuity comes from the epsilon delta definition. This theorem is saying that that definition is equivalent to saying f is continuous if and only if. So our definition means f is continuous if and only if f inverse v is open in X for every open set v and y. Okay, so let's first look at the picture and then we'll look at the proof. So what this is saying is X, it's Y. Okay, and these are again metric spaces, so we have metrics on them. Right? In a topological space, you would not have that. That's why you see here in the topological definition of continuity, it's written only in terms of open sets. Turns out you could define a function, what it means for a function to be continuous, without even mentioning anything about distances. Okay, so what it's saying is that if this function, so you have some function between them, f, if this function is continuous, right, on X, then if you give me any open set here in Y, so they called it V. If you give me any open set here in Y, then the pre-image, okay, the pre-image is red, which we denote by F inverse of V. Again, this does not mean the function is invertible. This means the pre-image of it, right? The pre-image of a set are just all the elements in the domain such that when you apply the function to that set, it maps to V. So the pre-image is just the collection of all points in the domain that gets mapped to V. Okay, so they're saying F is continuous if whenever V is open, the pre-image of it is also open. So if V is open, F inverse V will also be open. And this works for every single open set in Y. So if you take every single open set in Y, the codomain, and you pull back all of those open sets into X, all of those sets will also be open in X. Okay, so it's sometimes said that the pre-image of open set is open, or F pulls back open sets in Y into open sets in X. Okay, so that's what we're going to want to prove here. So let me just recall what the pre-image is, since we're going to be using it a lot. So the pre-image of, so let me use the same notation here, of V is just the set of points in X such that when you apply F to those points, you end up in V, right? It's just a collection of points in the domain that get mapped into V. That's the pre-image of V. Okay, so it's called the pre-image of V. Right, so sometimes we get lazy and we just say F inverse V, but of course, you should know it's not really F inverse, right? It's a pre-image. But if you slip up and you say F inverse, then we know what you're talking about, right? Of course, if F really is invertible, invertible means it's bijective, then it does have a pre-image. In that case, if F is invertible, the pre-image, instead of it being set with many, many points, the pre-image will just be exactly 1 point. Okay, so let's try to prove this direction first. Okay, so suppose F is continuous. I want to show that it pulls open set in Y back to open sets in X. So suppose F is continuous. Okay, continuous means the epsilon delta definition with respect to the matrix. So suppose F is continuous on X, and we're going to take V be an open set in Y. So V is an open set in Y. So we could say here, so we don't lose track of where we're heading, required to prove the pre-image of V is open in X, right? So there's quite a bit to keep track of. You have to keep track of where each of these sets live, which one is open where, and we'll be jumping back and forth between the domain and the codomain. So that's the only thing that makes this proof a little bit complicated, because you have to keep track of where are you? Are you in the domain? Are you in the codomain? How are you moving back and forth? But once you go through it a few times, and try to draw the pictures as you go through it, it will make a lot more sense. So that's what I want to show. I want to show the pre-image of V is open in X. So what's the usual way to show a set is open? I want to show that every point of F inverse V is an interior point. Okay, so let me take a point in the pre-image, right? And of course, this point belongs to, this point is over here, right? Oops. Right, so that's X. So let's take a point here. So I'll try to remember to update the diagram as we go along. So let X be an element there. Then, well, by the definition of the pre-image, if X is in the pre-image of V, then F of X gets mapped into V. That's by the definition of this thing. So X gets, let me take up this one, I'll draw this one. So X gets mapped into here. So this guy here is F of X, okay? So that's by definition of the pre-image. Now, what do I know about V? V is an open set. And maybe I should have drawn V bigger. Yeah, let me just draw 3 big. Because I'm going to have to put a neighborhood around it and stuff. Um, so yeah, let me take this to be B. Yeah, so that guy there is B. After inverse, let me make after inverse a little bit bigger as well. Right? Of course, I keep saying F inverse, but you of course know it's the pre-image. Right? Since V is open, or if you want, you could say open in Y, right? Then f of x is an interior point of V. Right? F of x is an interior point of V. Interior point of V. So what does it mean to be an interior point of V? It means that uh, there is some epsilon sphere or epsilon ball that you could put around this point f of x entirely within V. So that will look like, right? So V is open. So that means f of x is an interior point of V, which means to put an epsilon ball around it entirely within V. So we just need to write that. X is an interior point of V. This is we can find an epsilon bigger than 0 such that um, I see in the notes they use S for sphere. I was going to use B for ball, but better to keep it similar to the notes. So there exists an epsilon sphere of radius epsilon centered at f of x. And what is so special about this epsilon sphere? It's entirely within B. Okay, that's what it means to be an interior point. Now we could call this guy 1. Okay. Um, so that was the assumption that B was an open set. Now we could move over to the assumption that F is continuous, right? Because we need to use that assumption somewhere. Okay. So since F is continuous, right? At this point, X, right? F is continuous on the entire space X, so it's continuous at every single point. So since F is continuous at this point X, then given any epsilon, right? We already have that epsilon. So given that epsilon, so we could say then for this epsilon above, right? Well, we don't need to say above, right? You know, it's the epsilon that you just found with respect to that open sphere. Then for this epsilon, there exists a delta. So now we are applying the definition of continuity with respect to the metric space, right? The metric space definition. There, or at least our metric space, our definition for it in this course. There exists, right? I don't want to say that's the general definition for it, but it's one of them. And there exists a delta bigger than 0 such that, right? Such that if you take any other point um, in X, so let's take the point P, right? Any other point, and whenever the distance between this point, P and X, is within delta, from the definition of continuity, it means that the distance of their corresponding function values will be less than epsilon, right? That follows from the definition of continuity. So what we're saying here is that for that particular epsilon, there is a delta sphere or delta neighborhood over here, right? So I know I'm drawing it already inside of the preimage of V, right? So don't get, it will turn out to be this way, but don't get fooled by how I'm drawing it, that it always has to be this way. We have to prove that it is the way that I'm drawing it inside, right? But we'll see that it is indeed inside, right? Um, so they're saying that this is delta. So for that epsilon, there exists this delta, right? Um, such that on the next point they're calling P, right? So let's say this point over here, this is the point P, right? So whenever the distance between P and X are within delta, what happens? The corresponding image will be within epsilon. So I already have the image of X. So the image of P will be within this epsilon ball, right? So let me put this image of P over here. This is F of P. Okay, so whenever P and X are within delta distance, the corresponding image are within epsilon distance, right? That's what we just wrote down here. That's what all of this stuff means. Okay? And the corresponding distance is within epsilon distance. Now I just need to rewrite all of this in terms of open balls, or again, open spheres. So if we just look at the diagram that I that I drew here, it will tell us exactly how to write it. So from this diagram, well, we're going to write it down without needing a diagram, but from the diagram, we'll see where we're heading. So the diagram is basically telling us that if P is within this delta sphere centered at X, then F of P is within this epsilon sphere centered F of X, right? That's what this thing here is saying. So um, you could say hence um, P belonging to the sphere, the delta sphere centered at X, um, imply. So from the diagram, what do we see? We saw that the image was within the sphere radius epsilon centered at F of X, right? And of course, this epsilon sphere from one is in V, right? This epsilon sphere from one is in V. Okay. So what do I want to prove? I wanted to show that the preimage of V is open in X. So I wanted to show that every point of the preimage of V, X is in other words, I wanted to show X is an interior point of the preimage of V. So I need to construct a neighborhood around X that lies entirely within F inverse V. Okay, and the diagram shows me what that neighborhood should be. The diagram over here shows me that that neighborhood should be this delta neighborhood, right? That this delta neighborhood will be within the preimage of V. Now again, we need to prove this. You can't just draw the diagram and say that this delta neighborhood would have been inside of the preimage of V. I knew it will end up being there, that's why I drew it inside. But it could have been outside of F inverse V, the preimage of V. Right? For example, what I'm basically saying is, why did I draw the delta neighborhood inside the red circle and not like, for example, this? Why is it not outside of the preimage of V? That's what we need to argue. Why is it not outside there? Right? Uh, so we want to show, um, first we want to show that uh, this this delta sphere, if I say neighborhood, it's a sphere, by the way. I mean the delta sphere. This delta sphere is inside of this guy, right? That's what I want to show. This is what I want to show. Okay, so um, I already know X is within there, right? I already know X is within here. So if I just need to show X is within this guy, okay? Um, but I know that, yeah, so if X is in the pre-image of V, then that means that f of X belongs to V, right? So f of X we already know belongs to V. Uh, hang on. And just see, yeah, so we want to show that this guy is inside of this guy, right? That's what we want to show. And this is what I have. I have that f of p belongs to this sphere, which is in V. Oh, yeah. So it's all, yeah, so it's from right here. If if P belongs to this sphere, implies that f of P belongs to this sphere, then F, if I take F of this whole sphere, so where does this whole sphere map into? This whole sphere, therefore, maps into this whole sphere, right? Because if every value within this sphere, the corresponding function values within the epsilon sphere, then the function, then if I apply f to this entire set, that's going to end up inside of this sphere. Yeah, that's what I want to show. And of course, this sphere is within V. Okay, so if f of this sphere is within V, then that means that this sphere, put in delta, that means this sphere, delta sphere, belongs to the pre-image of V, right? Because every point here maps into V. So this set belongs inside of the preimage of V, and that's what I wanted to show. Yeah. Okay, so we could say plus x is an interior point of f preimage V. Let's say since x was arbitrary, um, since x was arbitrary, then this set is open because every point is an interior point. It's open. Okay, yeah. So the first direction, check. Okay. So now we need to just prove the converse. Okay. So now we want to prove the converse. This direction. So conversely, uh, I could say, suppose that the preimage of V is open in X whenever um, V is open in Y, right? So, so I'm required to prove that F is continuous at every single point on X. So required to prove F is continuous at any point in X, right? Using the epsilon delta definition. So that means let epsilon be bigger than 0. Okay, that's how we always go. So now I need to figure out a way to find a delta. Okay, so let epsilon be bigger than 0. And I'm going to take any point in X. Okay, so obviously the image of this point is obviously in Y, right? If you take any point in X, the image will always be in Y. So I need a way to invoke my hypothesis. I need a way to invoke that F pulls back open sets um, in Y into open sets in X. So I need to make an open set essentially in Y. Now I have a point in Y, f of x, right? I have a point in Y, and I also have a radius, epsilon, right? So why don't I just make an epsilon ball or epsilon sphere around this point in Y, because I know all open spheres are open sets. Okay, so consider the open set. Okay, so let me make an open set. I'm going to call it V because I know every open sphere is an open set of this radius centered at this point. Okay, and that's obviously in Y, right? So that's the open set in Y. Then by assumption, okay, by assumption, F is going to pull this open set back from Y into an open set in X. So by assumption, um, the preimage of this guy, which is equal to the preimage of, so lots of brackets, this one, close. So by assumption, this set is open in X. Okay, open in X. So we pull it back to X. It is open in X. Now, so essentially I need a delta, right? That's what I'm searching for, a delta neighborhood in X. So I have an open set in X, right? So let me just take this X that I have here, right? So clearly, since X, remember f of X is in Y, right? And sorry, f of X is the center of V, right? So f of X, this point is in the center of V, which means that X is obviously in the preimage of V, right? The preimages are all the points that get mapped into V. X is in the center of V. Oh, sorry, f of X is in the center of V. So obviously X gets mapped into V. So X is in the preimage of V, okay? And I know that this set, the preimage of V is an open set. So X is an interior point. So since X is in there, is an interior point, right? Because it's an open set. Um, there exists a delta, right? That's where the delta is going to come from. Remember, we are searching for a delta. That's where the delta is going to come from. There exists a delta such that there is a sphere of radius delta around this guy X, such that it lies entirely within the set. Okay, and the set is preimage of V. That lies entirely within the preimage of V. Okay. So now I need to take any other point, right? Because I want to show that f is continuous at every point in x, right? So now for any other p, any other point in x, and the distance between x and this point is less than delta. So if I take any other point p within a distance delta of this x, right? Then by definition, p will be within this ball, right? This ball consists of all points which are within a distance delta of the center x. So if I take a point P that have a distance less than delta to x, then P is obviously in this open ball, open sphere. So if P, and I know that this open sphere is within the preimage of V, right? So if P is in this open sphere, then P is also in the preimage of V, right? Because the delta sphere is within the preimage of V. So P is in this guy, means P is in the next one. So P is in there. Okay. Space. Maybe let me take this one on a new line. So this means that try that P is within there. Now, what was V again? Remember, V was this set, right? So let's replace that. So F, the preimage of V, what was V? V was the epsilon sphere centered at f of x, right? So P belongs to that set. So if P belongs, P belongs to the preimage of that set. So if P belongs to the preimage of that set, then it means that by definition of what the preimage is, it means that when I apply f to this value P, I'm going to end up inside that set. I'm going to end up inside this set. Okay, if P is in the preimage of this particular set, that means when I apply f to P, I end up inside of that set. That's what the preimage means. Okay, so if P is in this set, if P is in this epsilon sphere, then that means that the distance between the center, which is f of x, and this point, f of P, must be less than epsilon, right? So what do we just do there? So, so let's recap. We showed that for any point P, right, in x, if I take the distance between that point and x to be less than delta, then the corresponding distance between the function values will be within epsilon. That right here is the definition of continuity. Therefore, by definition, f is continuous at the point x. Right? And since x was arbitrary, f is continuous on x. Okay, so that's the proof that this metric definition of continuity that we have with respect to a metric is equivalent to the definition that comes from topology.